Hello everyone. I'm Kuromeru. The goal of Series02 is to learn about left-invariant vector fields and left-invariant differential forms. In this video, I'm going to talk about vector fields over several episodes. A vector field is something like the arrows representing wind direction on a weather map. You can imagine vectors extending from each point on a manifold. We can consider tangent vectors not only on n-dimensional Euclidean space but also on Lie groups. From the perspective of applications in physics, I'm going to set aside strict mathematical rigor and instead focus on how to use this concept. Alright then, let's get started. We'd like to start talking about vector fields. But before that, let me briefly mention a few points that confused me when I first learned them. First, we'll frequently use the term CR class function from now on. This means that the function f has all partial derivatives up to order r on its domain, and those derivatives are continuous. For example, let's take fx equals x times the absolute value of x. Then the derivative f prime x is like this. This function is continuous at x equals 0. But f double prime x does not exist at x equals 0. So f is a C1 class function, but not a C2 class function. Second, where do vector fields grow out from? They are defined on what's called a CR differentiable manifold, M. Let's assume that M is a smooth manifold of dimension, M. This means that for any point P in M, there exists an open neighborhood, U, around P, on which all derivatives up to order, R, are continuous, and U can be smoothly mapped via the coordinate map, phi, to an open subset of the real vector space, Rm. In short, even though M itself may be hard to describe using numbers directly, we introduce a coordinate system by establishing a smooth correspondence with Rm, in a way that preserves the meaning of differentiation. Third, vector fields originate at each point P in M. Every point P has an associated tangent vector space, denoted TPM. The basis of this space is written as partial over partial xip. We may often omit the subscript p for simplicity. From now on, let's refer to this as partial xi. Here, let's pay attention to the position of indices. Normally, coordinate indices are written as superscripts, like this, and the corresponding basis for partial derivatives is written with a subscript, as in E sub I equals partial over partial x I. This distinction will become important later when we start discussing differential forms alongside vector fields. Just to say this in advance, the reason for using different index positions is that they transform differently under coordinate changes. Superscript indices represent contravariant components, while subscript indices represent covariant components. This corresponds to the standard basis vector, E sub I, in Euclidean space, which has 1 in the component with index I and 0 elsewhere. Here, T means transpose. However, this is only an isomorphism, as vector spaces, addition and scalar multiplication correspond nicely, but their behavior under multiplication does not match. A vector field is a mapping that assigns a tangent vector from T(P)M to each point P in M, in such a way that the assignment varies smoothly. Because of this smoothness, a vector field can be thought of as a kind of continuous transformation. You can even imagine flowing along the vectors. Fourth, in the previous video, we talked about Lie groups. A Lie group is both a manifold and a group at the same time. So yes, it is a type of manifold. And just like with manifolds in general, we can define tangent vector spaces on Lie groups. Let's now look at a vector field on a Lie group. Consider the 2 by 2 Borel subgroup G defined like this. The standard basis vectors partial over partial x and partial over partial y then yield. These results might be surprising if you're used to working only with the ordinary Euclidean plane. The definition of tangent vectors we're about to introduce may look a bit complicated. However, it's an important definition, one you should always come back to when in doubt. Tangent vectors on an m-dimensional CR differentiable manifold M can be defined as directional derivatives along a curve CT on M. Let's assume C0 equals P. Using a curve C minus epsilon epsilon to U, where U is an open neighborhood of P. And any CR class function f u to R. We define a directional derivative x as follows. This means that the tangent vector x, when acting on f, returns the right-hand side. This is a coordinate-independent definition. By using our knowledge of partial derivatives in multivariable calculus, we can rewrite the expression on the right-hand side like this. We can also write it in a different local coordinate system. Since f is arbitrary, we can define x independent of f like this. This is an element of the tangent space. When applied at a point P, located at R, this can be interpreted as a velocity vector. When we express d over dt in another local coordinate system y, and apply it to R, it may appear as a different velocity vector. However, as long as the representation of R remains the same, it is actually the same object. This shows that x universally represents the velocity vector, regardless of the coordinate system used. The basis vectors of the tangent space are given by partial over partial x upper I. Finally, let's denote CR_M as the set of all CR class functions on M. Then X forms a vector space over the real numbers R. Let's verify the following for A, B in R and F, G in C, R, U. There are two key properties. One is linearity. And the other is known as the Leibniz rule. These are the algebraic properties of derivations. On the other hand, let's also take a look at operations between tangent vectors. As mentioned earlier, when we choose a specific coordinate system, it is natural to think of partial over partial xi as a basis of tangent vectors. The space spanned by this basis at a point P is denoted TPM. A general tangent vector can be written like this, with the coefficients ui being CR functions on U. Let x and y be elements of TPM, defined like this. When tangent vectors act on functions f, they satisfy the linearity of a linear map. Also, this can be written in the following way. Especially, AEI is an operation of this kind. Here, CT is, for example, like this. It shows that the tangent vectors form an R module. Since R is a field, they can therefore also be regarded as a vector space over R. In this video, we explored the concept of vector fields and tangent vectors. I hope this helps deepen your understanding. That's all for today. If you enjoyed this video, please subscribe to the channel and give it a like. Your support motivates me to keep creating more content. Thank you for watching.